Using pKa values to predict which side of an acid-base reaction will be favored works all the time. But finding those pKa values can sometimes be tricky. If they're not tabulated, you might need to do some kind of complicated calculation to find them or do an experiment. And it'd be a lot easier if we could just look at a molecule and predict whether it's going to be more acidic or more basic than another molecule. The way that we do that is by using this ARIO acronym, which we're going to talk about in a second. And what we do is we sort of evaluate the stability of various compounds. The more stable something is, the less reactive. So if I'm comparing two acids, whichever one of those acids is more stable is going to be a weaker acid. The one that's the least stable is going to be the strongest acid. The A for the ARIO acronym stands for atom. And when you're using this acronym, you need to make sure that you're using the A, R, I, and O in order. So the most important factor is the atom. What the atom tells us is the electronegativity and the polarizability of that atom and how well it can accommodate charge. So if we look at our first set of examples here, we have silicone, phosphorus, sulfur, and chlorine, all with a negative charge on them. All of these atoms are in the third row of the periodic table, and as you move to the right along the periodic table, elements get more electronegative. So chlorine is much more electronegative than silicon. What that means is that the chlorine atom is going to have a much easier time stabilizing that anionic charge, meaning it's going to be the weakest base, whereas silicon is going to have a much harder time with that anionic charge, so it's going to be the strongest base. If, on the other hand, we're comparing two atoms which are not in the same row, but they're in the same column, we use what's called polarizability. Right here we're comparing the halides, fluoride, chloride, bromide, and iodide, and fluorine being at the very top is going to be a very, very small atom. Iodine at the bottom of that list is a very large atom. Now, the larger these atoms get, the more polarizable they are, and the easier they can spread out that negative charge around the larger atom. What that means is that this I- is going to be the most stable anion, which means it's going to be the weakest base, whereas F-, the smallest atom, is going to be the strongest base. Now this is sort of interesting because it shows us why we have this strange behavior of the corresponding acids. Remember that HF is actually the weakest acid, and HI is a strong acid. And we can see why that is here. It's because the anions are correspondingly weak and strong bases. When you're looking at these types of relationships, it's always key to remember that if something is a strong base, its conjugate is going to be a weak acid, and vice versa. The stronger one thing is, the weaker its conjugate is going to be. If we're comparing two, let's say, bases, and the anionic charge is resting on the same atom, then we can't use the A for the atom to figure out which one's going to be stronger or weaker. So the second thing we look for is resonance. Now, what we have here is a series of nitrogen anions, and we have varying degrees of resonance. On the left-hand side, we have no resonance at all. The negative charge is fixed on that nitrogen. In the middle, we have one resonance structure where we can move this anion over here up to this oxygen, which is going to be pretty good because oxygen likes negative charges more than nitrogen does. And then on the far right-hand side, we actually have two resonance structures. We can move this negative charge to the right, or we can move it up here to the left. The more resonance structures an anion or a cation has, the more stable it's going to be because you're basically spreading that charge density over a variety of atoms. So each atom doesn't have to hold the whole charge all on its own. What that means is if there's more resonance, we're going to get a more stable compound, which means a weaker, in this case, base. And on the other hand, we have this compound on the left-hand side, no resonance structures, so it's the least stable, meaning it's going to be the strongest base. After trying to use the atom and the resonance terms to decide between acids and bases, if those don't work, then we can move down to I, which stands for induction. Now, induction is a lot less powerful than resonance, but it's a way, again, to stabilize a charge. I'm going to use an example here for these fluorine groups, and when you see fluorines, I want you to think induction, because they're the most electronegative atoms, so they really help stabilize negative charges and destabilize positive charges. What we can see in these bases here is they're all oxygen bases. They all have one resonance structure where the negative charge can move from one oxygen to the other. And the difference is that this CF3 group is moving closer and closer to the negative charge. Now, induction is a force where an electronegative element can pull electron density through single bonds. So it's very, very distance dependent. The number of bonds between the electronegative atom and the negative charge tell you how strong that induction is going to be. So on the right-hand side here, we have 1, 2, 3, 4 bonds to the negative atom, and then 5 and 6. So the species that has the CF3 closest to the negative charge is going to stabilize that negative charge the most, making it the weakest base, whereas the species that has the fluorine the farthest away from the anion is going to be the least stable and therefore the strongest base. If you've examined all the other factors and you still can't make a decision, then you can move down to O, which stands for orbital. Now I'm going to use alkane, alkene, and alkyne anions here to illustrate this. What we can see is that this species here has an sp3 carbon, an sp2 carbon, and an sp carbon. Now negative charges are more stable when they're on sp centers. And the reason for this has to do with the percentage of s character in those hybrid orbitals. Remember, an s orbital is a sphere and a p orbital has a node at the nucleus. That means that the s orbital, that negative charge, is able to get closer to the nucleus, which is positive, and become more stable. So the higher the s character, the more stable that charge is going to be. In this case, we have our sp orbital here. That's going to have 50% s character, and so it's going to be the most stable anion and therefore the weakest base. On the other side, we have sp3, only 25% s character, so it's going to be the least stable anion and therefore the strongest base.